So more application of Newton's law and how that applies to what we have technically already studied and what we are currently looking at within friction. And some of that comes within a uniform circular motion. What happens when objects are moving in a circle? More specifically, with a constant speed. We can't say a constant velocity because the direction is always changing. Because the direction is changing, the velocity is always changing. But we can say that it's moving with a constant speed. So that does allow for a little bit of that. Now, the velocity is tangent to the circle. Whether, and if it were over here, use one of the lightsabers, it would point in that direction. It'll go off straight off of wherever it is at that point. So if we had a ball and that it was moving, it would move tangent regardless of where it was at. Which then usually gets the big question, what would happen, to think about, what would happen if the sun were to just vanish magically? Because that's really what you'd have to kind of bring into account, is just like all of a sudden the sun vanishing magically, all of a sudden where would the planets go? Would they continue in their orbit, or would they continue on a straight path? So there is an equation for it. It does take into account radius, and that the acceleration of a circle, or centripetal acceleration, the time intervals are pretty small, but the radius of the circle is there. So the velocity squared divided by the radius. Now, as I swung the rope around, the radius of that increased. Therefore, it also increased a lot, and I spun it faster. The acceleration increased the ability for the force to also increase. So in all reality now, we can use Newton's second law, where force is equal to mass times acceleration, and now we have another way to bring in acceleration. Now the acceleration can be happening at a curve. And it gives you why does it feel like you're sliding out of well, here's the thing, back in the day we didn't always have as harsh as seatbelt rules. So you could be sitting pea shooter in the back seat of a car and slide to slingshot. This acceleration is called centripetal. Notice that it's a very commonly misspelled word. It's centripetal, not Centripetal. Okay? It's got the P in it. I always tell students that a centripetal is one that exists because F's are fake. Centripetal force is a feeling force, and feeling forces are fake. Bring us back to the sitting in the back seat of a car story. You're sitting pea shooter, so behind the driver, no seatbelt on, and the back seat is kind of a pleatherish thing, more of a vinyl. And you're taking a turn a little bit faster than it should be. The person with it's sitting behind the driver is going to move or slide across the back seat if they're turning right. You know, if the driver's taking a left-hand turn. Okay. They're going to slide across the back to behind the front seat passenger, what I call slingshot. Okay. Now, why are they moving outwards?
Their velocity is moving forward while the car is moving to the other side.
Exactly. They are wanting to maintain their straight velocity, and in doing so, you actually physically see that velocity maintaining straightness as that person in the back seat slides to the other side. So then, here is another scenario. The driver is now taking a right-hand turn. The person sitting behind the driver goes where? Into the vehicle, into the door, right? And you're like, wow, I'm really glad that door's there. Why? Because the door keeps you in. If that's the force that keeps you in the car. As we work through this, in 1 second interval, those red arrows move. Therefore, we could put them together, and the difference is, so, therefore, the acceleration is going to be pointing towards the center. The magnitude is kind of what you're dealing with. Kind of the reason why you're not dealing with tail to tip is the whole circular stuff. The angular motion has a kind of a different set of rules. That's when you use radians instead of degrees again. So there are some different rules, and that's why kind of looking at why not tail to tip. When we look at it, you would have the arc. So this here would be equivalent, if I can get it somewhat centered, to that there. Kind of the difference being able to kind of, you have just a smaller circle, so the arc should be equivalent. If you go tail to tip, you're trying to work with degrees and not radians. If we doubled the speed, we would have longer arrows, right? Doubling it out. as such. We would then look at what would that be? Well, now doubling the speed should make the acceleration 4 times bigger. Why would it make it 4 times bigger? Because according to the equations, if I put a 2 you would have 4 times, or it should be quadrupled, but that might change a little bit. But it's that square that's going to increase it, start to increase things bigger. What happens? So, just from a conceptual point of view, what happens when your denominator gets smaller? The acceleration gets bigger. Okay? Because now if we look at these put together, because they have a tighter circle, that difference becomes greater as well. We see that is the change. So as that radius gets smaller, the acceleration also increases. So to put the equation in a more formal thing, the acceleration part of the equation is really, in a way, you are just putting that acceleration, substituting the acceleration, the centripetal acceleration, in to the centripetal force, because the acceleration points to the center, so does the force. To finish everything off, to make sure that we all get it all down, for an acceleration always will point towards the center of the circle. If there is an ellipse, that means there's going to be more than one center because there's more than one focal point. But for circles, which we will deal with mainly in this class, that is where the acceleration will point, because the acceleration points towards the center, the net force will also point towards the center of the circle. It is called centripetal force as opposed to centrifugal force, which is spelt with an F, and we don't want to deal with anything that is fake. So centrifugal force is a fake force, where centripetal force is what we will talk about with those forces that deal with circles.